Hello everyone, in this video I'll be showing you how to generalize the stars and bows problem. So some of you might be wondering what the stars and bows problem is, and I'll show you what it is through this small scenario. So let's say I have 10 pieces of candy, and I have 3 kids I want to split them between. Now for this problem, we're going to assume that the candy, it's the same, right? So they're all like Kit Kats, or they're all like Smarties or whatever. It's the same type of candy, so it doesn't matter what type each kid gets. We're just worried about what amount of candy each kid gets. So let's imagine the first kid. I just call that kid Alex, and Alex is gonna get 3 pieces of candy, for instance. Now the second one, Ben, he gets 4 pieces, and the third one would have Carol. She gets 3 pieces, right? So 3 plus 4 plus 3 equals 10, and that means that all 10 pieces of candy have been split between these 3 kids, and, well, the problem's solved. Well, another solution could be maybe Alex gets 2 pieces and Ben gets 5 instead. Or Alex might even get 0 pieces and Carol gets 5. These are all valid solutions. So the problem is asking, how many ways are there to split these 10 pieces of candy between the 3 kids? So if, for instance, 0, 5, 5 is a way, we can also have 0, 0, 10. That is also a valid solution to this problem. Now I'm going to make a diagram to show how this problem can be thought of. We're going to imagine these 10 pieces of candy are stars. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is where the stars in the name stars and bows comes from. Now we need to split these stars between the 3 kids. So for instance, we can have Alex, he's getting 3 pieces, so we can represent it like this. What did I call him? Ben, I think, gets 4 pieces, and Carol gets 3 pieces, right? So this is just an alternate way of thinking of this problem. And we can represent this by drawing bows between the stars. So you'll see here is I have drawn bows between these stars, and now I have split them into sections. So this first section is Alex's section. The second section is Ben's section, and the third section is Carol's section. So you can see Alex in this diagram has 3 pieces of candy, Ben in this diagram has 4 pieces of candy, and Carol in this diagram has 3 pieces of candy. So now the clever thing about this diagram is we can now move the bows around. Let's say we move this bow right here, and we change where Ben is, right? So now, if we look at this diagram, Alex now has 1, 2, 3, 4, 5, 6 pieces of candy, Ben has 1 piece, and Carol has 1, 2, 3 pieces of candy. So now the problem becomes, how many ways are there to put these 2 dividers between these 10 pieces of candy? Seems simple enough. And if you've taken any sort of probability classes, you'll know there's a function called combinations. And combinations are just the number of ways to arrange something without worrying about order, without worrying about types. And this is exactly what we're needing in this problem. Since we don't care about the order of the candies, we just worry about where to put these 2 bows. Now let's remove these labels, and let's take a look at how we can solve this problem with combinations. There's 10 pieces of candy in total, and you'll see to divide these 10 pieces of candy into 3 containers, we are using 2 bows. So 2 bows, they're dividing these 10 pieces of candy into 3 containers. So we realize is the number of bows needed to divide these things into 3 containers, or n containers in general, is always, actually I think using the letter k would work better here. It's always k minus 1. So where k equals the number of containers, the number of bows we need to divide them into these containers is k minus 1. we have 1, 2, 3 sections, we have 2 bows. Alright, now let's say n is the number of objects that we need to split among these containers. So in this problem, we have 10 pieces of candy, but we're going to generalize it to n, right? And if we want to use combinations to solve this problem, we're going to need to figure out how many ways there are to put these 2, or k minus 1 bars inside this total. So what's the total here? Well, we can actually just add the number of objects with the number of containers minus 1. If you take a look at how many symbols I have here, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 objects, and I'm adding on these 2 bars that are used to split these objects into containers. So, the number of total symbols there are in this problem is n plus k minus 1. And you can start to see why this is. We have n things, we have n objects, we're adding it to k minus 1 containers, and that's the total number of symbols. And then we can choose k minus 1 bars out of them. We're choosing 2 places to put these bars out of these 12 symbols. So this is actually our solution for when we can have like any number of objects giving to any number of containers. So this is, I'm just gonna call it solution 1. Actually, solution for min 0. And you'll see what I mean in a second here. Now, let's take a look at a different type of problem here. We still have 10 pieces of candy, and we still have 10 kids, but each kid has to receive at least 1 piece of candy, right? We don't want to make any kids feel bad, so we have to give each kid at least 1 piece of candy. So again, let's put out the 10 stars. Let me see if I did that correctly. Yep, that's 10. But now, we need to put the bars so that there's always 1 piece of candy in between them. So you'll see here that, well, this section has 1 piece of candy, this section has 4 pieces of candy, and this section has 5 pieces of candy. So an invalid solution to this problem would be something like this. Since Bob, or Ben, I think what I called him, now has 0 pieces of candy, and now Ben feels bad. We can't do that. We have to have at least 1 piece of candy for each kid. So how can we solve this? Well, a way to solve this is actually just to remove the 1 piece of candy that each kid must receive. So if you were passing out these pieces of candy, a clever way to do this would just to be give 1 piece of candy to each kid and then split the remaining 7 pieces of candy among the kids. So we can simplify this problem by just removing the 3 pieces of candy that each kid has to have. And now we have the same exact problem, but instead with 7 pieces of candy, and the number of bars still stays the same. So basically, we're just removing the pieces of candy that each kid already needs. And you'll see here, if we generalize this for n number of objects and k number of containers, we have the solution for when minimum equals 1. And this is going to be the number of objects. We're going to need to subtract k. We need to add k minus 1. And I'll explain this in a second. And we need to choose k minus 1 out of these. So what does this mean? This seems like a lot here. But what you can see is n is the number of objects, right? And we're subtracting k from these. Now k is the number of people there are, so we're just giving the 1 that each kid needs to have. We're just giving it away in the first place, so you don't need to worry about it later on. If you were passing out these pieces of candy, you would just give each kid a piece of candy. Sorry, I can't talk right now. You would just give each piece of candy to each kid. And that's the minus k right here, because we need to give away 3 pieces of candy for each kid. And again, we're adding k minus 1 because that's the number of below 0. So this is the total number of symbols in this scenario. And we're just subtracting k because that's the piece of candy that each kid needs. And then k minus 1 is constant always because it's just the number of balls that we need to put in. And you'll notice that this is actually really nice because we can actually simplify this. The k's cancel out and we get n minus k, choose k minus 1. I mean n minus 1, choose k minus 1. Since these k's, they just cancel each other out. But there's a reason I left it like this. You'll actually notice that once we start increasing the number of, like the least number of candies you need to give each kid, the problem changes in a similar way. So here I have 10 pieces of candy again, and then we're gonna have dividers between them. These bars in between these symbols. Now, let's say in this new scenario, scenario 3, each kid has to get at least 2 pieces of candy. So, 1 piece apparently isn't enough, we have to give each kid 2 pieces of candy. Well, we can solve it the same way we did earlier. We remove the 2 pieces of candy from each kid, and now we're left with this, which is the same exact problem as our solution for a minimum of 0. And what I just basically did right here is I gave each kid 2 pieces of candy from the start. I gave each kid 2 pieces of candy in the very beginning, and then now we don't need to worry about it anymore. Oh, there's some error in Bash right now. I'll worry about that later. So our solution for the minimum of 2 is now n minus 2k plus k minus 1, and we're going to choose out of that k minus 1. And you can see why here. This 2k right here, that's just the 6 candies we removed. We took away 2 pieces of candy for each kid. And then we have the same for both sides. We have the k minus 1, which is the number of bars. We have n, which is the number of objects in the beginning. And you might start to see a pattern here. If I just put these in parentheses, where this is the number of, like, the number of objects we have remaining after we've handed out each piece of candy to the kids. Now the pattern here, if I remove this, is we basically subtract 0k for a minimum of 0. So if I put minus 0k here, which doesn't change it, because 0k is just going to be 0, so n minus 0, it's not going to change anything. And if I put 1k right here, that doesn't change anything either. You can start to see that the general solution is n minus however many the minimum is, times k, plus k minus 1, choose k minus 1. So now if we make a new variable here, we call it m equals the minimum number of objects for the container. We can now have the general solution, which is n minus mk plus k minus 1, choose k minus 1. And that is the general solution for the stars and bows problem. Leave a comment below if there's anything that I didn't explain so well. I probably had trouble explaining this. And as always, thanks for watching, and see you in the next video.